In this video, we're going to go over regression preliminaries. We'll talk about what regression is and what some of the main objects and elements are of regression. So at a basic level, regression is a modeling task if the response y is known and if it is numeric. This is an example of a supervised learning problem. Y is part of the data set. You've measured it. There are many kinds of regression that you may meet. We'll just be talking about ordinary regression, but there's also logistic regression and Poisson regression that are slightly different and used for different scenarios. In regression, x is usually continuous, but this is not a requirement. Usually we discuss it assuming that it's continuous, but in practice it is very often categorical and then converted to a numeric value. When we use the term simple regression, we usually mean that there's one response and one predictor. Simple in this sense means that it's not complicated. It doesn't mean that it's easy. Now, the basic idea with regression is that the response y is going to be some function of the predictor x for some partially known function f of x. And I'll explain exactly what that means very soon. But right now, we can just think that a model is a proposed formula for f of x, which we don't know, but we do know it up to some unknown constants. And those unknown constants are going to be denoted beta. As a general rule of thumb, when you see Greek characters used in statistics, it means that those are unknown quantities. The unknown quantities are usually referred to as parameters. And since the function f of x depends on beta, we'll usually write it like this. Y equals f of x with this vertical line here. That vertical line is read given. Or sometimes people, and this is a little bit older notation, they'll use a subscript next to the f to denote that this function, i.e. the formula that is used for the function, also depends on beta in addition to the x. Now, to understand regression, we really need to talk about data and error. At a basic level, we're given a data set that is a combination of pairs of values, xi, yi, for I going from 1 to n. In other words, these are the observations that we have. The observations that we have are two different measurements, or at least two different kinds of measurements. One we're calling x and one we're calling y, and in our sample, we have n individuals. Each one is simply labeled 1 through n. So if I'm generically referring to one of the observations in the data set, I would refer to it as xi, yi. For example, in a study of people's heights and weights, xi could be the height of the ith person and yi could be the weight of the ith person. If we're looking at water measurements, xi could be the pH of the ith measurement and yi could be the dissolved oxygen content of the ith measurement. The image that we have in mind here is something like this. When we make a scatter plot of each of these points, each point is an individual observation, and we could actually label them. So for example, if the data set looks like this would be the standard representation of the tibble. Notice that I have x1, y1. That's going to be some observation there in the data set. For example, it could be this one. So x1, y1 is that dot right there. x2, y2 is that dot right there. And maybe the nth one is right there. So every dot is just a different labeled value. This is an observation from the data set. This is also where f of x comes into play. F of x is equal to y in some generic form. F of x is associating together the pair of response and predictor variables. And it takes the form of a simple curve. Now, we don't actually know that, and we refer to it as the true relationship between x and y. Now, in this generic sense, a simple regression model is some model that is of this form. So there's some response value, that's yi, and it's equal to the function f applied to xi plus some term over here. The term on that side, epsilon I, is something that's unknown. It's actually not a parameter, but it is unobserved. And it's used to collect various errors. Now in this setting, we don't know f of x, but we refer to it as the systematic component. We also don't know the epsilon i's. Those are usually referred to as the random component or the noise in a particular model. In statistical modeling, epsilon is given some probability distribution, and the epsilon i's are assumed to be independent draws from that distribution. For example, in the ordinary linear regression model, each epsilon I is drawn from a mean zero normal distribution independently of one another. And the way that we would usually write this is something like this. yi given xi, meaning somebody tells you what xi is, and you're interested in what is the distribution of yi, that is normal with a mean of f of xi and a variance of sigma squared. Of course, sigma squared is not known, but xi is given to you. As a consequence, the model looks like this. If this is f of x, that's the actual relationship between the response and the predictor that we're interested in. Every point that we observe is going to be considered to be one draw from a random distribution that's going to kind of bump you off of that line. So for example, for this first point, there's a distribution that's centered on the line, and the draw from that distribution is going to be the epsilon I. It's going to bump you off of it. And the same thing goes for every single point. Now, if you kind of tie these together, you can kind of imagine that there's a kind of underlying band of high probability that's around the line that it's most likely the points are going to fall into it. Now, this is somewhat misleading because it looks like the band just cuts off and you can't see points like this one. But in fact, you can. This is more of a tapering effect that diminishes in probability as you move away from the line, not something that drops off. So usually we refer to these as probability intervals, or in a slightly different sense, confidence intervals. But the idea is that you demarcate some certain high probability region, and that's exactly what we've done in this particular situation. In ggplot2, these are created by the geom ribbon function. So those are all the regression preliminaries we need. We're ready to move into mathematical preliminaries.